podcast, we're going to discuss Vesper theory. Vesper stands for valence shell electron pair repulsion theory. It's an attempt to explain the three-dimensional shapes of molecules. The whole premise behind Vesper is basically that electron pairs want to be as far apart as possible. Electrons are negatively charged, and so when you get pairs have opposite spins so that they can be close to one another, but then when you get two sets of pairs close to one another, they repel. So we want to make them as far apart as possible to minimize the repulsion. All right, we've been drawing Lewis structures so far, but they don't show us geometry. They only show us the arrangement of the electron pairs. But we can use special lines to illustrate 3D molecules on a 2D sheet of paper. Dashed lines will be bonds that are going into the paper, and wedges will be bonds that are coming out of the paper. So if you look here, we have a 3D molecule. Here is a 3D picture. We see we have this back bond that is going into the page, which is going to be this dashed hydrogen over here. And then we have one that is coming out, and that will be this wedged hydrogen right here. And then these two hydrogens shown here in the picture are in plane with the paper. All right, we're going to use special formulas when we're talking about Vesper to better understand what's going on. We're going to use the letters A, X, and E. Now on your paper we use A, B, and E. B and X are interchangeable. They mean the same thing. A is our central atom. X would be any outer atoms or any electron pairs that are attached, and then E will be the lone pairs of atoms, or lone pairs of electrons that are on the central atom. All right, so here's some examples of the formulas. So if CO2, we see that he makes double bonds with two oxygens, and we see that on the central atom, C, we only have two things attached. So 1, 2, because the double bond only counts as one. So that would be AX2. Now in this one, H2O, we still have two things attached, so it's still AX2, but now we also have these lone pairs on there as well. So it's going to be AX2E2. And then on this last example, I3, 1 minus, still have two things attached, so that's still AX2, but now we have three lone pairs, so that gives us an AX2E3. All right, so let's start with the first example. All right, in class and on your sheet, you are expected to be able to do both the electron geometry and the molecular geometry. Electron geometry, you're just looking at what's coming off the atom and not really caring if it's another atom that it's attached to or if it's a lone pair. Okay, so we have AX2, which is our CO2 example. Here is the structure just shown in AX form. And here we have the same thing. Now, we see that we only have 1, 2 things attached, no lone pairs. So it's going to be AX2. And then when you look further at the molecular geometry, you see that both of the X's are actually atoms, so it turns into an AB2 or AX2. So it's linear. So there's nothing else that it can be but linear. Okay, so linear electron geometry and molecular geometry, when you have an AX2, it's going to be the same thing. So you don't have two separate things like you do in the others. All right, now when we move on to different geometry, AX3. AX3 is the electron geometry. So anything that has three things coming off is going to have an AX3 electron geometry. So here in this example, we have 3 atoms that are attached to the central. So that's an AX3 electron. And then on this one, we also have an AX3 electron geometry because there are 1, 2, 3 things still coming off. Okay, so they both have an electron geometry of AX3. Where it gets different is the molecular geometry. On the first example, the SO3 example, we see that every single thing that's coming off of it is a bond to another atom. So that means that its electron geometry and its molecular geometry are the same. So that's a trigonal planar geometry. If you have no lone pairs on the central, your electron geometry and your molecular geometry will always be the same. But we see down here on SO2, we have a lone pair. That changes the molecular geometry. So we have AX2, and then we have an E. Okay, that gives us a bent configuration. Okay, like this little shape over here. Now if we look here, here's the trigonal planar, and we see that the bond angles are going to be 120 degrees. Okay, so there's 120 degrees between these. All right, when you're looking at the bent configuration, you would expect there to also be 120 degrees between this because we have 1, 2, 3 things coming off, same difference. But this electron pair is actually going to push these two bonds down more, closer together, due to the repulsion that that lone pair gives. And it's actually going to make their geometry or their bond angle be 105 degrees. So it decreases the bond angle, this electron pair. So it pushes these down. Okay, or up here, it pushes these X's down. Okay, so this is a configuration called bent, but understand that bent is the molecular geometry, and the electron geometry is still AX3, the trigonal planar. All right, the next set is the AX4 family. All right, AX4 is the electron geometry, and if you have no lone pairs on the central, it'll also be your molecular geometry, like in the example of CCl4. Okay, this is called tetrahedral. Now, if you have an AX4 electron geometry, but you have one lone pair, then that means that you have a trigonal pyramidal. You have an AX3E, okay, where you have these three going down like the base of a pyramid, and this lone pair up here that's going to push the bonds down a little further. And then the last one you can have with an AX4 electron geometry is an AX2E2, which means you have two lone pairs on the central and two bonds going to other atoms. Very common example is H2O. Okay, so let's look at these a little bit more. So here's our AX4 example. We see that it has bond angles of 109.5 degrees between each of the hydrogens. All right, and then when you throw a lone pair in there, that is going to decrease your bond angle to 107 degrees because this electron pair up here is pushing these down closer together. And then when you have two electron pairs, like in the case of a water molecule, an AX2E2, it pushes those bonds even closer together. So now you have a bond angle of 105 degrees between the two waters. But remember, because there are four things coming off, it still falls in the AX4 electron geometry family. Okay, so far you've seen two different ways to get bent molecules. Okay, so you see that many things can be bent even if they have a different electron geometry. All right, the next family is going to be the AX5s. The AX5s are called trigonal bipyramidal. And if we have no lone pairs, we're going to get the same molecular geometry as electron geometry as you see over here. Now, if you have one lone pair on the central, you get what's called a seesaw formation. Okay, so that's four bonds, four atoms attached to the central, and one lone pair. Good example, SF4. All right, and the last one that we see here is going to be AX3E2, where you have two electron pairs on the central. Gives us a molecular geometry that is called T-shaped. You see that it is in the shape of a T. All right, and the very last one is going to be AX2E3. This is where you have three lone pairs coming off the central and then two bonds. This gives us a linear formation. Okay, so you see that there are more than one ways to get linear. You just have to be careful with that electron geometry. Now, if we look a little further, AX5, the trigonal bipyramidals, have bond angles of 90 degrees and 120 degrees. So 120 degrees will be here, and then the three that are on the same plane, they have 90 degrees separating them. Okay, Seesaw Formation, where you have the 1-electron pair. We're still going to have the 90-degree angles between on these two, and then we're still going to have the 120 degrees. So this 1-electron pair, he doesn't have enough repulsion to actually change any of the bond angles in this example. Okay, T-shaped, where you have 2 electron pairs on the central atom. They're going to give you bond angles of 90 degrees. So you'll have 90 degrees every direction. Okay, all right. And the last one, linear, it's going to have a 180-degree bond angle, just like linear did in the very beginning example. All right, the very last set that we have are the AX6s. AX6 is called octahedral, and if you have no lone pairs, you're going to have the same molecular geometry, and you'll get this lovely looking shape over here. If you have one lone pair, you're going to get what's called a square pyramidal. So it's like the square base of a pyramid right here, and then you have this one bond sitting off to the top. If you have 2 lone pairs on the central, like in XEF4, then you're going to get just the base of the pyramid, which is called square planar. Okay? All right, so here we have octahedral, our AX6. All of the bond angles are going to be 90 degrees. Here we have the AX5E, which is the square pyramidal. They'll all have 90-degree bond angles. And then here's our square planar, and they'll all again have 90-degree bond angles. Okay, so you see that the more constituents you have coming off the atom, the less the electron pairs are going to affect the bond angles. When you had very few pairs, as in the beginning examples, you see that it affected the bond angles much more. All right, so here's a summary of all of the bond angles. You can just remember this, and then remember that if you have a lone pair, it will decrease that bond angle. Like here, if we had a lone pair here, this would make our bond angle less than 120 degrees. Then that will greatly help you on the test. All right, same thing here. If this was an electron pair, our bond angles would be less than 109.5 degrees. Okay, so here is what I've been talking about the whole time about the lone pairs. So here we have an AX3 molecule. They have bond angles of 120, but when you take that top atom, the oxygen, and replace it with a lone pair, you see it pushes down more on these bonds, and we have a decrease in the bond angle. Okay, so anytime you put a lone pair up there, it's going to decrease your bond angle. All right, what if you don't have a central atom? Say you have 2 central atoms. Well, you can still predict geometries. You're just going to have to do it piece by piece. You're going to have to talk about each atom separately as central atoms. All right, this Vesper model, how well does it work? Well, it does an outstanding job for very simple, for such a simple model. The predictions are almost always accurate, but it always has a few exceptions. Anytime you're dealing with odd numbers of electrons, Vesper is not going to be as good of a model to look for. You have to get a little more complicated to deal with that. All right, and if you need any more help, you can go to this website, www.kimmybear.com/shapes.html, and it will show you a bunch of different animated images that you can manipulate, and they're clickable so you can rotate them and learn more about them. And that's Vesper.